Hello students, I am Dr. S.M. Bhatti. The objective of this video is to introduce Laplace transform and its inverse transform. Let f of t be a given function of t which is defined for all positive value of t. That means the interval for t is 0 to infinity. If integral 0 to infinity e raised to minus st ft dt exists, then you can call this integral as a capital F of s, and the capital F of s is called as Laplace transform of function small f of t, and in this way we can have this equation. We suggest Laplace transform of the function small f of t is equal to capital F of s, and it is integral from 0 to infinity e raised to minus st ft dt. Here t is a variable of integration, s is a parameter which is a constant during the integration, and this s may be the number, right? Here ft is a given function, capital F of s is it's a Laplace transform, and if capital F of s is a Laplace transform of small f of t, then small f of t is called as inverse Laplace transform of capital F of s. Actually, this capital L is an operator. It transforms a function of t to function of s. It is clear from this equation. It transforms a function of t to function of s. And here we use small letter for function of t. We use capital alphabet, corresponding capital alphabet for function of s. This L is called as Laplace transform operator. And if you change the side of this capital L from left to right, it became L to L inverse. And in that case, we can have another equation, that is L inverse of capital F of s is small f of t. Right? So here is the important point. Laplace transform of function small f of t is a capital F of s, while inverse Laplace transform of the function capital F of s is small f of t. That is Laplace transform function of t to function of s, while inverse Laplace transform transforms function of s to function of t. Note that s is a real or complex value or number. Now we'll find Laplace transform of some standard function. Here is example. Find L of cos omega t. That means find the Laplace transform cos omega t. So there you have to apply the above definition. Put f of t as a cos omega t in the definition. You can have Laplace transform of cos omega t is equal to integral 0 to infinity e raised to minus st cos omega t dt. Here t is a variable of integration, s is a constant, omega is constant. You can observe that the right hand side, this right hand side has a type, this integral, and hence we have to make use of this formula. The difference between the formula and the right hand side is one is the t, here t, u is a variable of integration, here t is a variable of integration. Here limits are alpha and beta, here limits are 0 and infinity respectively. Then here role of a is played by minus s and role of b is played by omega. So when you apply this formula, you can have this kind of step. L of omega t, L of cos of omega t is equal to e raised to minus st in the bracket minus s cos omega t plus omega sin omega t upon omega square plus s square with the limit for t 0 to t is infinity. First we put t is infinity. But when you put t is infinity, we have to assume that s is a positive. because when s is a positive, it became e raised to minus positive into infinity, that became e raised to minus infinity, and that is 0. It is known to us. Otherwise what happened? Otherwise means if s is negative, then you will find here e raised to infinity, and e raised to infinity is infinity. That's why we have to here add a condition that s is greater than 0. Otherwise what happened? E raised to minus st at t is infinity became infinity, that is diverges. So the Laplace transform of cos omega t is s upon s square plus omega square if s is greater than 0. So when you do actual calculation, integration calculation, you find you have to think of the existence of that solution, right? So here we have to add a condition if s is greater than 0. Let's find now Laplace transform cos omega t. Let's find it now. So Laplace transform cos omega t, cos omega t is a standard function. So if you apply definition of Laplace transform, Laplace of cos omega t became integral from 0 to infinity e raised to minus st into this cos omega t dt. Now here, uh, instead of applying that previous definition, we apply here integration by parts. Let's try to find the value of this integral by other technique. So we apply integration by parts. Take the sine omega t as a first function and e raised to minus st as second function. So when you apply integration by parts, you have this first function sine omega t as it is integration of second function e raised to integration of e raised to minus st is e raised to minus st into minus 1 upon s, and it has a limit t equal to 0 to t equal to infinity plus they say next term we have minus sign, and there you have to write the this derivative of first function integration of second function. But what is the derivative of sine omega t? It is omega cos omega t into this minus minus became plus e raised to minus st upon s can be taken to the outside the integration because s is a constant, and you'll find this kind of step, right? But you can see the here this integral is nothing but the Laplace of cos omega t, and just now a few minutes back we obtained Laplace transform of cos omega t, and it is a we obtained that. So we when you put that value as a s upon omega s square plus omega square, you can see s will get cancelled and you'll find omega upon s square plus omega square. Let's find now Laplace transform t raised to n. Okay, here n is n number, right? And in between we may get certain condition on n also. So let's find Laplace of t raised to n. If you apply the basic definition of Laplace transform, it is a integral from 0 to infinity t raised to n e raised to minus st dt. Further we put t as a z upon s. That means we are converting the variable that t to z. Okay, s is a constant here. So that dt became dz upon s, and this integral became like this, and which is this. Here you can see that in denominator s has a power n plus 1, so you can take 1 upon s raised to n plus 1 outside the integration, and you can see this integral. You have seen this integral in the previous course. It is actually gamma of n plus 1. This is nothing but gamma of n plus 1. If you apply the property of gamma function, that is if you apply this definition, the difference is here actually here we have n, and here we have x minus 1. Here power of t is x minus 1, so here we have x, and here t is a variable. Difference is here z is a variable and z has a power n, so this is actually gamma of n plus 1. So in this way we obtain Laplace transform of t raised to n, and if n is a natural number like a 1 2 3 4 and so on, in that case gamma of n plus 1 became n factorial. So same formula we can write as a Laplace of t raised to n equal to n factorial upon s raised to n plus 1. So actually we have two formulas. For one formula is Laplace of t raised to n. If n is a natural number, then it is a n factorial divided by s raised to n plus 1. And otherwise we can have this formula, Laplace of t raised to n is gamma of n plus 1 upon s raised to n plus 1. And we can prove some standard result like Laplace of 1 is 1 upon s, Laplace of e raised to at is 1 upon s minus a. If you apply definition, easily you will find this kind of results. Let's see the important property of Laplace transform, that is a linear property. Fine. This is a theorem now which represents linearity of Laplace transform. Laplace of constant a into ft plus b into gt is equal to a L of f of t plus b L of g of t. Okay, let's see example to understand this. We know Laplace of e raised to at is 1 upon s minus a. So using this definition, Laplace of e raised to at is 1 upon s minus a. Can you obtain the Laplace of sin h of at? Yes, we can obtain it. Look at here. By definition, sin h of at is e raised to at minus e raised to minus at upon 2. And now you apply linear property that we have shown above. We can split this Laplace in two terms and apply this formula. Laplace of e raised to at is 1 upon s minus a here. First term became 1 upon s minus a. Second term became 1 upon s minus of minus a, that is 1 upon s plus a. And when you make a cross multiplication, you will find this. So this is nothing but Laplace of sin h of at. Now let's you must understand that inverse Laplace transform also satisfies linear property. Let's see small example. Find the L inverse, that is inverse Laplace transform of s upon s square minus a square. Now s upon s square minus a square can be factorized using the partial fraction method. We can have this, and here you can apply linear property. When you apply linear property, you will find first term became 1 upon 2, and inverse Laplace transform of 1 upon s minus a is e raised to at, while the second term became 1 upon 2, and inverse Laplace of 1 upon s plus a is e raised to minus at. And adding these two terms, we can have this, and which is nothing but cos h of at. So in this way, we have shown that inverse Laplace transform of s upon s square minus a square is cos h of at. Here we have used partial fraction method. We have used also we have used standard formulas of inverse Laplace transform, and those formulas are obtained from Laplace transform, no doubt. Now I can show one table. So this is a table where the first column represent different standard function of t. So I can take them as a f of t. I can write them as a f of t. This is a f of t. Fine. So first column represent different function of t, standard function of t, like a 1 which represent constant function. Second, e raised to at, t raised to n, that is a polynomial. Sine of at, cos of at. Here a is a constant, n is a number. Okay, so the first column represent a function of t. The second column, you can see a second column represent corresponding value of their Laplace transform. So a second column represent Laplace transform of, I can make here square bracket now. You can see I am using pain function here, but it is not working properly. Okay, so Laplace transform of f of t. Fine, now it's working. That is, or I can say capital F of s. So first column represent small f of t, and second column represent corresponding capital F of s, that is Laplace transform of small f of t. So you must remember these all the formulas, by heart them and use them. So while using these formulas, we have to use, if required, you can use linear property and use these formulas to find Laplace transform of some composite functions, right? So these formulas can also be used while obtaining inverse inverse Laplace transform also, right? So you can see last entry here, cos h of at. A is constant. That means Laplace transform of cos h of at is s upon s square minus a square. Also, Laplace transform of cos at, a is constant here. It is s upon s square plus a square. Likewise, inverse Laplace transform of s upon s square plus a square is cos at. So this table is very basic, very important, very useful. For this video, we have used two books here. One is B.S. Gravel and second is from S.R. Sapre sir, B.S. Wage sir, myself and Ravi sir. Thank you very much for watching this video completely.